Swayam Prabha. Digital India. Educated India.
and for molecular weight plus we also need to the gas constant for each of this component. But rather if you use in terms of moles, the advantage that you will get is the consideration of mole fraction and number 1. Number 2, instead of gas constant we can get this information through universal gas constant. Now, when you do this analysis, there are two types of analysis when deal with the listing the mass fraction for the components of the mixture. We call this as analysis as gravimetric analysis, and the corresponding listing in terms of mole fraction is called as molar analysis. So, in our study we will deal both the things, like we can think about gravimetric analysis as well as the molar analysis. Many times molar analysis of the mixture is also called this volumetric analysis. And other important point is that we need to find out the molecular weight of the mixtures. So, one way to do that is by considering through their respective mole fraction or mass fractions, and knowing their molecular weight of each individual components, one can find out the apparent or average molecular weight of the mixtures, and it is defined as the ratio of total mass of the mixture to the total number of moles in the mixture. So, whatever I have discussed so far, this is represented in mathematical form in the slides. So, what it says is that we have a mixture containing number of gases 1, 2, 3 and J. Each gas will have number of moles as N1, N2, N3 and Nj. And the total mole of the total mass of the total number of moles in the mixture is N, and this mixture occupies a volume V, and the mixture exists at temperature T and pressure P. So, if under these situations, if you want to calculate, one can calculate the total number of mass, which is the summation of Mi, total number of moles, which is the summation of Ni, mass fraction MFI, that is equal to Mi by M, and summation, of course, the summation of all mass fraction is unity. Similarly, mole fraction we can define as Yi, that is Ni by N. Of course, the summation of Yi is also 1. Then we can find out the molecular weight of the mixtures. So, total mass of the mixture is M and number of moles is N. So, that is equal to, so we can say what is the molecular weight of the mixtures, and these numbers we can also find out by taking summation of Yi into Mi. Yi is the mole fraction for component I, Mi is the molecular weight of the component I, and this we can get it through this, because M is equal to M1 to M1 plus M2 plus Mj divided by N. Each M is N1 and M1 plus N2 and M2 and so on. So, likewise we get the summation of the Yi and Mi as the molecular weight of the mixture. So, this is how we calculate the apparent weight or molecular weight of the mixture. For example, if you treat air is a mixture of nitrogen, oxygen, argon with this percentage, then one can find out the molecular weight by taking care of the relative weightage or compositions, and we all know that this number is molecular weight of air is 28.97. So, this is how the mixture composition was analyzed. Then we will move to pressure, volume, temperature relation for the mixtures. So, till this point of time we all know that pressure, volume, temperature relations for pure components. Now, these pure components form a mixture. So, if the mixture behaves as if it is were a pure component and it consists of so many other pure components, then how you are going to deal with. So, the first model that is proposed for this analysis is the Dalton's model. So, what this Dalton's model tells that and this Dalton model is mainly used for an ideal gas model. What is the advantage of this model? Because it gives a simplified mathematical treatment which can fit appropriate for all the mixtures. Now, beginning we have assumed that the mixture behaves as an ideal gas as well as the pure components. Now, when we say it is ideal gas model, at that point of time the first assumption that we make is that the molecules exert negligible forces on one another and the volume occupied by the molecule is negligible relative to the total volume occupied by this gas. Now, considering these two things, that means in the absence of significant intermolecular forces, the behavior of each component is unaffected by the presence of other components. At the same time, the volume occupied by the molecules is very small as compared to the total volume. So, the molecules of this gas thus can be regarded as to free to roam around throughout the volume. So, the Dalton's model takes this advantage of these considerations and they proposed a concept what we call as a partial pressure for the component of the mixture. So, considering this Dalton's model which is consistent with the above concept, it is assumed that each component behaves as an ideal gas as if it were alone at the volume and temperature of the mixture. So, he defined this partial pressure of the component Pi is the pressure that its composition Ni moles would exert if it were at volume V and pressure P of the mixture. But the component Pi is the partial pressure of the component in the mixture. If this component with certain composition Ni is present in the mixture at a volume V, that means P and V is the total volume, V is the total volume of the mixture and the P is the total pressure of the mixture. So, in that way the partial pressure for the component I is defined. To some extent, and it is a special case for additive pressure rule. Now, when you frame the additive pressure rule in your previous slides, it was main concentration was on the multi-component systems, but whereas the Dalton's model is only for the ideal gas scenario. So, as a result what we see is that Dalton's model is a special case for additive pressure rule relating pressure, specific volume and temperature of the gas mixture, and is also a specific case for an ideal solution. Then ideal solution is referred as Amagat model. Amagat model means it allows additive volume rule. So, additive volume rule gets simplified as Amagat model and additive pressure rule gets simplified as Dalton model for an ideal gas. Now, considering the same concepts, we did it for calculation of mole fraction, mass fraction, molecular weight. We will try to see how to find out the partial pressure of the component. So, in a mixture, this mixture behaves as an ideal gas model. So, we can use this ideal gas equations P is equal to N R bar T divided by V total volume. Then this equation we can write it for the component I. Only change that is going to happen is the number of moles in that component, rest of the numbers remain same. Now, so we can find a ratio Pi by P is Ni by N, nothing but Yi. So, thus Pi is equal to Yi times P. And now if you take the summation of this Pi, it is going to, we are going to get summation of Pi is as P, which is nothing but your additive pressure rule. In same line, if you calculate the partial volume for the component I Vi, we can write Ni R bar T by P, and if you take the ratio between Vi and V, we will also get the mole fraction, and taking the summation of the individual volumes, then we will get the total volume. So, this analysis also satisfy the additive volume rule, and this molar analysis we call this as a volumetric analysis of the mixture in terms of mole fractions. Now, having said this, we have individual component in terms of partial pressures, and you also find out what is the volume of each individual component. Now, knowing all these things, we are now in a state that we can find out, and we also know mass fraction as well as mole fractions. So, we can find out other properties of the mixture. Other properties I mean internal energy, enthalpy, entropy, specific heat. And thermodynamically, we can view this as a closed system as shown in this figure, where there is no mass and energy interaction is taking place, and from there we can find out the extensive properties U, H and S from these relations. So, with same philosophy, internal energy of the mixture is the sum of internal energy of each component. U is equal to summation of Yi, Ui, and U can be regarded as number of moles into U bar. U bar is the specific molar internal energy. So, Nu bar we can find out summation of, or we can find out U bar is equal to summation of Yi into Ui bar. In the same line, we can find out enthalpy of the mixture H is equal to summation of Hi, and H bar, small h bar is equal to summation of Yi Hi bar. Entropy of the mixture S bar is equal to summation of Yi into Si bar. Specific heats, that is specific heat at constant volume, Cv bar, which is nothing but du bar by dt. Then we know what is u bar, so we can find out du bar by dt. Then specific heat at constant pressure, that means it is a molar specific heat, Cp bar, dou h bar by dou t at constant pressure, which is equal to summation of y into Ia into Cp bar I. So, with this we are in the end of the discussions that how you are going to evaluate the thermodynamic properties of the mixtures. With this line, let us try to solve some numerical problems which we have understood from this lecture. So, let us understand the first problem which states that the molar analysis of gaseous products of combustion for hydrocarbon fuels are listed as carbon dioxide as 0.07 fraction and water as 0.1, oxygen at 0.08, nitrogen at 0.75, and if you add them together you will end up having the total fraction as unity. So, this is nothing but your molar analysis. Now, we are asked to find out the molecular weight of the mixtures and prepare a gravimetric chart. So, basically when you talk about gravimetric chart, we need to convert this molar analysis value to their respective mass fraction and see that if the total mass is unity or not. So, to start this, first thing what we know is the mixture composition in terms of molar fractions: carbon dioxide, water, oxygen and nitrogen. And then we can find out this then what we can do is, like, we can prepare a chart consisting of component, then its mole fraction, then when you multiply with respect to molecular weight we get mass fraction Mi, and then number of moles, when we multiply it by molecular weight we get its mass. Then from this we can also find out what is the mass fraction. Okay. So, we have CO2, whatever data it is given, it is given as 0.07, and this molecular weight of CO2 is 44. Then we have water, its value is 0.1, molecular weight is 18. Then oxygen, its fraction is 0.08 and its molecular weight is 32. Then we have nitrogen, molar fraction is 0.75 and its molecular weight is 28. Now, when you multiply them you can find out what is the mass. Mass will be 3.08 for CO2, 1.8 for H2O, 2.56 for O2, and for nitrogen it is 21. Now, if you sum it off of this, Ni is 1.0, and then when you summation of Mi will get 28.44. Then we know this Mi, summation of Mi, then Mfi is nothing but Mi by total mass. So, 3.08 by 28.44, 0.108, 1.8 divided by 28.44, 0.063, 2.56 divided by 28.44 will be 0.09, and 21 divided by 28.44, 0.739. So, if you sum it off, this summation is also 1.0. So, you can check your molar analysis also gives 1, summation of Ni is 1, and this mass fraction analysis also gives Mi is 1. So, this analysis is correct, and this is called as gravimetric chart. That means, we converted molar chart to gravimetric chart. Now, if data is also given in the gravimetric form, we can get back to molar chart as well. Now, what is left with this apparent molecular weight? So, apparent molecular weight we can calculate. So, we know each of this molecular weight and their number of moles. So, we can write it as 44 into 0.07 plus 18 into 0.1 plus 32 into 0.08 plus 28 into 0.75. So, then we can find out apparent molecular weight for the mixture is 28.44 kilojoule kg per kilomole. So, this is nothing but this data. So, this problem demonstrates about gravimetric chart and molar analysis or volumetric chart. The next problem is about evaluation of pressure exerted by the mixture under the consideration of different rules, like one is through ideal gas equation, other is K's rule which we studied earlier, third one is Van der Waals equations, fourth one is additive pressure rule. And this additive pressure rule also closely resembles with the Dalton's model. Okay. So, now we will try to evaluate them one by one. So, what the data that is given, a mixture consists of 0.8 kilomole of methane and 0.274 kilomole of butane, and it occupies a volume 0.24 meter cube and temperature 238 degrees centigrades. So, you can recall that we have a container consisting of a mixture and it occupies the total volume and temperature as 238 degree centigrade. This total volume is 0.24 meter cube and temperature is 238 degree centigrade, and that is nothing but 511 Kelvin. And this mixture contains 0.18 kilomole methane, that is CH4, and 0.274 kilomole butane. Butane is C4H10. So, based on this we can find their respective molecular weight. Now, first thing that we need to find out what is the total number of moles. N is equal to N1 plus N2. Now, if you sum it off, this is 0.454 kilomole. Now, then we can find out what is Y1. Y1 stands for methane, Y2 stands for butane, C4H10. So, we can find out Y1 is equal to N1 by N, that is equal to 0.396, and Y2 is equal to N2 by N, that is equal to that number will be 0.604. So, these are the common data we get. Also, we know volume, so we can find out molar volume. V bar is equal to V by N1 plus N2. V is 0.24 meter cube. So, it is 0.24 by N1 plus N2, that is 0.454. So, this number is 0.53 meter cube per kilomole. And we also know R bar is equal to 8314 joule per kilomole Kelvin. Now, let us start the first model. First model is ideal gas. So, ideal gas model says that we write the equation P is equal to R bar T divided by V bar. So, we all know we know these parameters T, R bar, V bar and T, and by inserting these values we can write this, and this R bar is joule. So, we have to convert them into bar. So, 8314 into 511 divided by V bar 0.53, since it is in joule we have to divide it by 10 to the power 5. So, this will give P is equal to closely 80 bar. So, ideal gas model predicts that pressure exerted on the by the mixture will be 80 bar. Then K's rule. K's rule talks about the calculating the value with respect to critical parameter for the mixtures. So, for each mixtures we need to find for each component, first thing we need to find out the critical pressure and temperature for like for methane and butane, and subsequently we have to find out critical pressure and temperature for the mixture. So, let us say for CH4 we know that we have to use the data table, and that data table is available in any of the thermodynamics books at the end of towards the end. So, for methane we can say TC1 is 191 Kelvin, PC1 is 46.4 bar. For butane C8H10 TC2 425 Kelvin, PC2 is 38 bar, and for each case we know Y1 is 0.396, Y2 0.604. So, then we can find out for mixture. For mixture we can write TC is equal to Y1 TC1 plus Y2 TC2, and this value will be turn about 332.3 Kelvin, and similarly PC we can write it as Y1 PC1 plus Y2 PC2, and this number will be 41.33 bar. So, we have PC and TC, but this PC and TC will not talk about pressure calculations. So, we have to find the reduced parameter. So, this reduced parameter means we find to find out TR. TR is nothing but T by TC. So, T is your 511, TC is 332.3, this number is 1.54. Then we have VR, that is V bar T or PC PV by R bar TC, and V bar already we know 0.53. So, VR number would be 0.794. So, TR and VR then will give you Z is equal to 0.88. How? You have to use compressibility chart. Okay. So, through compressibility chart we get Z, but knowing Z we require P. So, Z we can write it as P V by N R bar T. So, all the number we know, what we do not know is P. So, V by N is 0.53, temperature is 511, then we can write P is equal to Z into R bar T by V bar. By inserting this value we can write P is equal to 0.88 into 8314 into 511 divided by 53 into 10 to the power 5, because you are converting it to bar. So, this calculation will give you P is equal to 70.4 bar. So, K's rule gives P is equal to 70.4 bar. Okay. So, we have ideal gas, we have K rule. Then we have to go for the van der Waals equation model. Now, this van der Waals equation model, first thing we have to say that what is the van der Waals equation of state, and in fact, this van der Waals model is one form of the real gas model. So, we can write P is equal to R bar T into V bar minus B minus A by V bar square. So, V bar we already know 0.53 meter cube per kilomole. Now, what you do not know is A and B. R bar is already known, what you do not know is A and B. To do that, we have to find for each case, like for CH4 we need to find from the data sheet what is A1, it is 2.293, B1 0.428, we also evaluated Y1 its mole fraction 0.396. Then we have C8, C4H10, that is butane. For this data sheet will give A1 as 13.86, B1 as 0.1162. Now, from your previous data or problem data, we already calculated what is mole fraction, Y2 is equal to 0.604. Now, having said this, we can find out A is equal to Y1 A1 to the power half plus Y2 A2 to the power half. Why I said half? Because this A is, if you look at this equation, the empirical relation shows that it is related with V bar as A by V bar square. So, as if we have taken the square root of A1. So, considering this, the effective number for A for the mixture we get as 8.113, and B is equal to, B will be Y1 B1 plus Y2 B2. Then after this, by putting this number and inserting the values, we can get for van der Waals gas model will give the mixture values, the pressure exerted by the mixture as 66.9 bar. Okay. And last one is additive pressure rule. Now, the additive pressure rule says that we have to treat each mixture component as individual component, calculate its critical values, then correspondingly you find its compressibility factor, and then you calculate the effective compressibility factor. Then from this effective compressibility factor you have to calculate the pressure. To do that, what we have to do is that we have to first calculate the reduced parameter for butane and methane. So, reduced parameters we can say for CH4 we can get TR1 as T1 by TC1. Already we have noted down TC1 value earlier. So, it is 191 by 511, this number is 2.69. And similarly, we can calculate what VR. VR is V1 bar PC by R bar PC. So, V1 is 0. That is V by N1 into PC by R bar TC1. Then this VR number would be 2.61. So, TR1 is 2.61 and VR will be PC1. VR1 is 2.69 and VR1 is 2.61. This will use compressibility chart and this gives Z1 is equal to approximately 1. Similarly, for butane C4H10, we know what is TC2, that is 425 Kelvin. We know PC2, that is 38 bar. Similar procedure will be followed and this will give you TR2 is equal to 1.2, BR2 would be 0.95. So, these two data will give you Z2 is equal to 0.95. So, individual compressibility factor for the components we know, that is for methane it is approximately 1, that means it is as if a ideal gas, and for butane it is 0.95. So, effective compressibility factor, so you can say Z is equal to Y1 Z1 plus Y2 Z2, and this number we can write is 396 into 1 plus 0.95 into 0.604. So, this value would be 0.88. Then we can write general equation, that is PV by N R bar T is equal to 0.88, and this equation will give you P as 70.4 bar. So, if you can see that this is the same value what predicted by K rule. So, if you make a comparison of P is 80 bar, which is predicted by ideal gas. P is equal to 70.4 bar, which is predicted by K rule and pressure rule. And this P is equal to 66.9 bar by van der Waals model. So, of course, it is a real gas model, and if you see the problem defines that experimental value is 69 bar. So, what we can say is that the van der Waals gas model being a real gas approximation, its prediction is closer to experimental values. But however, based on the simplicity, we are using ideal gas model, and based on our choice and advantage of the using different concepts, we can use the other models like K rule and pressure rules. So, this problem demonstrates that how the pressure of the mixture can be calculated by variety of considerations. Okay, with this I conclude this lecture for today. Thank you for your attention.